Look closely at the internal mechanics of a legacy telecommunications switching system. This purely physical network transfers information by routing voltages through complex mechanical relays. In this analog baseline, data exists as a smooth variation of voltage or current traveling over a physical copper wire. But physical transmission has an unavoidable vulnerability. The further an analog wave travels through a medium, the more its energy dissipates. As the signal weakens, it accumulates systemic noise. Thermal energy, ambient interference, and random voltage spikes permanently attach themselves to the traveling wave. You can attempt to restore the signal strength with an analog amplifier, but because an amplifier cannot distinguish between intended data and ambient static, it amplifies the noise exactly as much as the signal. A degraded signal was acceptable for voice communication, but as computing emerged, that error rate became fatal. Computers require an environment of flawless data exchange. To guarantee absolute fidelity across a network, engineers had to abandon the transmission of continuous physical waves entirely and rebuild the architecture around discrete mathematics. Digital modulation is the process of transmitting a digitally modulated analog carrier signal between two or more points in a communication system. This architecture provides a core operational advantage: noise immunity. Instead of reading a continuous voltage, the hardware evaluates whether the signal crosses a specific threshold. The random noise is sheared off, and the signal regenerates as perfectly sharp binary pulses. Converting information into discrete digital states allows computers to perform digital signal processing. Hardware can execute complex algorithmic filtering, phase shifting, and error correction that analog systems cannot handle. These discrete packets of data also maximize network efficiency. They are inherently adaptable to time division multiplexing, allowing multiple separate signals to be woven together and transmitted simultaneously over a single channel. But this architecture demands a basic physical cost. Transmitting sharp, square binary pulses requires significantly more frequency bandwidth than sending a smooth analog curve. By sacrificing bandwidth, engineers secure mathematical certainty, a certainty generated through the mechanics of data conversion. This flowchart outlines the analog-to-digital conversion pipeline. To execute the conversion, the hardware relies on three rigid stages: sampling, quantization, and encoding. The goal is to take an infinite, continuously variable physical reality and map it into a finite set of discrete mathematical bins. The pipeline begins with sampling, which discretizes time. The hardware measures the exact instantaneous voltage of the analog signal at strictly regulated time intervals, denoted as T sub s. The required frequency of these measurements is governed by the Nyquist criterion. The formula states that the sampling frequency must be at least twice the highest frequency component in the original signal. If the sampling rate drops below that limit, known as undersampling, the system breaks down. Captured data points connect to form a completely false, slower wave. This is aliasing. It creates a false, low-frequency signal that permanently corrupts the data. To prevent aliasing, modern networks operate well above the Nyquist minimum. Systems typically oversample by a factor of 2.5 to 3 to accommodate the roll-off of physical anti-aliasing hardware filters. Sampling arrests time, instantly locking a chaotic physical wave onto an exact rigid grid to guarantee perfect frequency retention. This stage illustrates quantization. While physical reality offers infinite voltage values, digital hardware operates on a finite number of states. The hardware divides the total voltage range into discrete steps. The magnitude difference between these adjacent steps is called the resolution. Resolution is calculated by dividing the total voltage range by 2 to the power of n, the system's bit depth. The hardware forces the infinite analog value into the nearest finite bin. A sampled measurement of 11.7 volts snaps to the exact 12-volt line. This action creates a mathematical difference between the actual sampled value and the quantized level. We call this discrepancy quantization error. Within the system, this forced rounding error behaves identically to additive white noise. It alters the signal's true amplitude. Reducing that error requires finer resolution steps, but doubling those steps means exponentially increasing the bit depth, which demands significantly more complex integrated circuitry. Engineers can implement workarounds like companding, applying a logarithmic compression curve that assigns finer steps to low-amplitude signals and coarser steps to louder ones. Ultimately, quantization is a calculated compromise. Engineers accept a known, mathematically defined noise floor in order to achieve the stability of discrete states. The final stage is encoding. The system must translate the quantized levels into a syntax that computers can transmit and store. It is a direct translation, assigning a specific binary code word to each quantized sample level. This formatted output sequence is defined as pulse code modulation, or PCM. For baseband transmission, these bits are sent as physical pulse waveforms. For wireless transmission, the bits are used to modulate a high-frequency radio carrier. This exact PCM encoding logic forms the bedrock of modern digital media. It is the architecture that allows hardware to execute playback without analog degradation. Encoding completes the transition. It strips away the variance of physical waves, reducing the signal to pure mathematical syntax. Eventually, the data reaches its destination. For digital information to be consumed as a physical phenomenon, like audio from a speaker, the mathematical syntax must be reconstituted into analog form. This block diagram illustrates the digital-to-analog converter, or DAC. It receives the incoming sequence of binary numbers. For each binary word it processes, the DAC outputs a strictly proportional electrical voltage. The output is a stepped approximation of the original wave. It contains the correct data, but the strict voltage jumps generate unwanted high-frequency switching edges. The signal must pass through one final hardware component, a low-pass filter. Because the original Nyquist parameters were strictly maintained, the low-pass filter easily isolates and strips away the high-frequency jagged edges. The physical wave emerges intact. The total system architecture successfully captures an analog reality, translates it into a mathematically shielded state, and regenerates it across any distance. By mastering the rigid thresholds of sampling, quantization, and encoding, engineers expend massive bandwidth to transform a fragile physical signal into indestructible mathematics.